As you're coming in, we're going to do a live experiment. So if you go to this URL, it's also on the whiteboard over there. Go to the URL, you're going to do a one-question survey, and then that's going to take you to the notebook where you'll see all the analysis for the talk. So let's get started. I'm Alan Downey. I teach at Olin College, which is a new engineering school outside of Boston. Well, 20 years old, so maybe not that new anymore. But we're trying to fix engineering education. What I'm talking about today is the inspection paradox, and I'm going to explain using a first example, which is, suppose I want to know the average size of families in the US, and I have a convenience sample, which is the audience at PyData. So my first thought is I could ask you, how many children do you have? But a lot of people at the conference are kind of young. Your families are probably not complete at this point. So if I want complete family sizes, all right, I've got a good idea. This is going to turn out to be a bad idea, and I'll explain why, but here's my good idea. I'm going to go up a generation. So instead of asking you how many children you have, I'm going to ask how many children your mother has. So that's what the survey does. And again, if you go to that link, it'll take you to this survey, and I'm going to fill that out. Survey.
Your one question is biased.
So my mother has 3 biological children. And now I'm going to go to this notebook, and hopefully this will allow me to analyze the results. If you haven't used Colab before, this is one of a number of environments where you can host Jupyter notebooks, and they're executable. I found it very helpful. If you haven't used notebooks before, the key thing to know is Shift-Enter. That is how you execute cells. And if you just hit Shift-Enter a few times, we'll run through the analysis. Oh no, it's not written by Google. That's okay, you can run it anyway. So on Colab, you're in a virtual environment, and you often have to install things each time you start up a notebook. And you can also reach out to Google Sheets, which is where the results went, and grab the data. Looks like I've got a bunch of nans there, but there's probably some good data in there too.
Yeah, it's just the first 10 rows.
Got it. So that's what the distribution looks like. Lots of single children, lots of two children families, a few 3s, a few 4s. 7 is the biggest number so far. Interesting. Big family. I put in a little check here in case anyone was going to mess with me and put in like 300. So anything bigger than 20, I'm going to not believe you. And the mean, in this case, turns out to be 2 1/3. Okay, interesting. So of all the families that I just surveyed, the average size is 2 1/3. But in the US, the average lifetime fertility is really close to 2 at this point. So what I'm seeing is that this group seems to come from a more fertile family than average. And we could start to ask why. And you might think, well, it's an affluent group, it's a well-educated group, we could think about race and ethnicity. All of those things might be true, and that might make the average higher or lower, but there's one other really big factor that's in play here, which is if you come from a family that has no children, you're not here. So families with 0 children are not represented in this room, and actually it's worse than that. Families with many children are overrepresented. It's kind of like a lottery where the more children you have, the more probability you have of being in this room. And in general, if a family has X children, it will be overrepresented in this sample by a factor of X. That's an example of what's called length-biased sampling, where your probability of being in the sample is proportional to some kind of size or length or duration in time, usually in a linear way. And that leads to the inspection paradox, which is that if you do subtly different kinds of sampling, you get surprisingly different results. This happens a lot. It is not a super well-known thing. It's known by some different names, but a lot of people haven't heard of it. Once I tell you about it, you are going to start seeing it everywhere. So brace yourself. Now, this is often a problem, like you can be wrong or misleading because of this, but it's also an opportunity, which is sometimes you can do clever experimental design and take advantage of it. Here's another example. Class sizes. If you go to a university or a college and you ask the teachers how big their classes are, you might get an average like 31. If you ask students how big their classes are, you might get an average of 56. And you might think that somebody's got to be lying, but they're both right. They're just reporting averages over a different population. And one of them might be more descriptive of the teacher's experience, and one of them is more descriptive of the student's experience. So it's not that they're wrong, they're just measuring different things. You just have to be careful about what you're measuring and how you report it. So I didn't make up those numbers. This is from Purdue. They published the distribution of class sizes from a few years ago. And you can see this example. There were 138 students who took a class that had one student in it. It must have been an independent study or something like that. But there were 333 classes that were 100 or more students. So if you're walking around campus, there are only 138 students who will report to you that they are in a class with one student. But there are 33,000 students who are going to tell you that they're in a really big class. So you're going to greatly oversample large classes, and again, it'll be oversampled by a factor of the size itself. So I grabbed their summary statistics and I kind of filled in the blanks with some random number generation to get a fake sample of actual class sizes. And then I used kernel density estimation to try to get a smooth picture of what that distribution looks like. So very roughly, if you talk to the dean and they gave you the actual distribution of class sizes, this is roughly what it would look like. And now, this is the technical content of this talk. If you have the unbiased distribution, you can compute what would this look like if I asked students by doing weighted resampling. So I'm going to use NumPy random choice to generate a new sample from the actual sample that I collected. The new sample is going to be the same size. So n is the same size as the original sample. It is sampling with replacement, so some values will appear more than once, other values might not appear in the resample. And it's weighted in the sense that I'm going to take the given weights, normalize them so that they add up to 1, and pass them into NumPy as p, this parameter which is the weights. So now if I have the actual class sizes, that's what unbiased is, I'm going to pass in the sample of unbiased class size, and I'm passing in the class size as the weights. So I'm weighting the distribution using the values themselves as weights. That's the key. If you understand that, you understand this entire talk. Let's see what that looks like. Again, the blue is the unbiased view from the point of view of the dean. That's the actual distribution of class sizes. The orange is what it looks like for students. It greatly underrepresents small classes and greatly overrepresents large classes. So again, this is potentially a problem if you accidentally measure the wrong thing, but it's also an opportunity, which is, let's say that your school doesn't publish the distribution of class sizes and you want to know what it is. You could go around campus and you could ask students. Now, you know you're getting the biased view, but given the biased data, you can apply the inverse of that weighting in order to estimate the actual. So here's what I'm doing. This is the sample here is pretending I'm walking around campus and I interview 500 students and I ask them how big their classes are. And then I'm calling the same function I called a minute ago. I'm passing the sample as the first parameter, but now as the second parameter, it's not the values, It's the inverse values, because I'm doing the opposite direction. I'm unbiasing the data. So now here's what that looks like. The blue line is ground truth. That's what the actual distribution is. The orange line is the biased sample that I got when I walked around to ask students. And then I applied the inverse filter to the orange line, and I got the green line. The green line is a pretty good estimate of the actual distribution. It's particularly good for larger class sizes. It's a little bit less good for small class sizes because those are hard to sample. There aren't very many people around to report small classes. So I would need a pretty big sample in order to estimate that part of the distribution well. But on the whole, this works. So anytime you're not able to get ground truth data, sometimes you can back it out from a biased sampling process. Okay, once you become aware of this phenomenon, you start to see it everywhere. So airline passengers are always complaining because the flights are always full. Airlines are always complaining because they're flying empty planes around and losing money. Who's lying? Possibly neither of them. If the flight is really full, there are a lot of people there suffering. If the flight is nearly empty, there are very few people who will report how much they enjoyed the extra space. How come when you call the call center, they are always experiencing higher than normal call volumes? Because the number of people who experience that is a lot. Same reason you can't get a taxi. This is a really interesting article. This is from 2012 talking about taxis. And there's a new startup company that we're talking about that they thought was really going to help with this. Uber. Another example of the same thing. You are waiting for the bus in the rain, and you talk to the public transit company, and they say that the buses run every 20 minutes on average. So if you arrive at a random time, you would expect to have to wait about 10 minutes on average. That's not true. In fact, you end up waiting longer because there's some variability. Sometimes the buses are close together, sometimes they're farther apart. If there's a big interval between buses, you are more likely to arrive during a big interval than a small interval because it's bigger. And it's this linear weighting again. Your probability of falling in any interval is proportional to the length of that interval. So I got some data. This is Kendall Square on the Red Line in Boston. And the MBTA publishes live data that I downloaded for about a week and collected the time between trains at Kendall Square during rush hour. And sometimes they end up really close together, like 2 minutes, and sometimes they're spread out about 16 minutes apart. This is what it looks like if you are the MBTA. That's the Massachusetts Bay Transit Authority. They run the Red Line. But if you're a passenger and you arrive at a random interval, this is what you see. And I did this the same way. By weighted resampling of the unbiased distribution, I got the orange biased distribution. So it's shifted off to the right. And sure enough, the MBTA will insist that the average is 7.8 minutes, and passengers will insist that their average is longer, and they are both correct. They are just averaging over different things. Now, in this case, the difference is not huge because the variance is not huge. As the variance gets bigger, the effect of this biasing gets much bigger. And there's one extreme example of this. So let me ask you a question. Are you popular? The answer is no. And there's science. There's a reason the answer is no. This is actually from Scientific American. So you know this is true. This is the friendship paradox. And that is, if I pick you at random, and then I pick one of your friends at random, the chances are about 80% that your friend has more friends than you do. Which seems paradoxical. But think about what a social network looks like. So think of it as a graph. Each node is a person. Each edge or each line is a friendship between two people. This graph, by the way, I didn't make this. I just found this at random on somebody's blog. So first of all, thank you to them. But second of all, weirdly, so my name is Alan. My wife's name is Lisa. I have no idea who Liz is. If anybody asks, neither do you. So one more time, if you think of this as a graph, if you choose a random node, and then choose a random edge and go to its destination, and then for that node you ask how many friends it has, the probability that you land on a node is proportional to the number of edges that lead to that node, which is the number of friends. So a node with degree x, or number of friends x, is oversampled by a factor of x. Now in this case, the distribution of friends is highly variable, so this is going to make a really big difference. This is a data set I grabbed. This is the Stanford data sets for studying networks. They got some data from a social network company in, I think, like 1998. It just had 4,000 users at the time, but they got the number of friends for each of them, and this is what that distribution looked like. So there are a few people that have hundreds of friends and lots of people that just have a small number of connections in this social network. So this is highly variable. And if I now do the friend sampling process, again, I'm going to overweight popular people. There's what the biased distribution looks like. So people with a small number of friends are almost invisible in this sampling process. People with hundreds of friends show up over and over because of the way I'm sampling. And it has a big effect on the mean. In this example, the actual average is about 42 friends per person. But if I do this pick a person and then sample a friend process, the average is about 100. So a really big difference. Once you know about this, you start seeing it everywhere. And if you're running a 200-mile relay race, you have a lot of time to think about this. So I ran this race, and I noticed that whenever somebody overtook me, they just blew past me. They were really fast runners, like Colin. But when I overtook people, I was flying past them. And my first thought is, okay, maybe this is like a weird race, and it attracts a bimodal distribution of runners. Maybe slow runners and fast runners like relay races, but people in the middle like me just don't do this format. So there's nobody else out here running at the same speed as me. By now, you have probably figured out that that is not true. Because of the way this format works, the runners are spread out over the course, so it's almost a random sample of different speeds. But if you're out there and running, the people that you see depend on how fast you are running. If you run fast, you are likely to overtake slow people. If you run slow, you will be overtaken by a lot of fast people. And in general, the probability of observing another runner is proportional to the absolute difference between their speed and yours. So this is a little bit of a variation, but it's still this linear relationship between the size of the thing that you're measuring and your probability of observing it. So the actual distribution of running speeds is just unimodal, but you are applying a notch-shaped filter to it, which is the absolute value of the difference between your speed and theirs. And so the result is a distribution that appears to be bimodal. So let's get some data on this. I didn't get data from the actual relay I ran, but I grabbed a 10K that's near where I live, and this happens to be my 10K PR. I just wanted to put that up there. It's personal record for you people who are not runners. Steve. So here's what the actual distribution looks like. Now, interestingly, it is not a normal shaped distribution. It's not a bell curve. It is skewed out toward fast people, which is kind of interesting by itself. So now I'm going to take this and use my biasing process to see what this would look like if I were running at 7 miles an hour. I'm actually faster than that, but at 7 miles an hour, what you see is what appears to be a bimodal distribution. Okay. Now, mathematically, it would go to 0. It's not doing that here, in part because I'm using KDE, and that's kind of smoothing over the 0 part. But that's also probably more realistic because you vary in speed a little bit. You have some chance of seeing somebody running at your speed, but just a lower chance. So that's what that looks like. This happens on the highway, too. If you're not a runner, you are likely to see fast people. You are likely to see slow people. You are unlikely to see those sane, safe drivers like yourself, regardless of what speed you're going. Once you see this, you start seeing it everywhere. So I read Orange is the New Black a while back, which is very different from the television show. This is a memoir of a woman who went to a federal prison for about 17 months. And one of the things that comes up over and over in the book is she was very surprised by the length of the sentences that her fellow prisoners were serving. Now, first of all, she's right. So this is the incarceration rate in the United States over the last 100 years, and this is a national disgrace. So Piper Kerman, the author of the book, is absolutely correct. However, she is also being somewhat misled by the inspection paradox, which is if you arrive at a prison at a random time and you pick a random prisoner, you will oversample prisoners in proportion to the lengths of their sentences. The longer they're there, the more likely you are to observe them. So we can get data on this. This is from the Bureau of Prisons. They actually update this monthly, so you can get a distribution of imposed sentences for the current population in prison. So this is a case where the data that they are publishing is already length biased because it is based on a snapshot of the current prison population. So they are oversampling long-term prisoners and undersampling short-timers. However, we can take the bias data and apply the inverse filter like this. Now, in this case, federal prisoners typically serve about 85% of their nominal sentence. And at the federal level, there's actually not very much variation on that. By and large, you get a sentence, you serve 85% of it. So we can use 85% of the nominal to figure out the actual time, and then apply this inverse filter one more time. So there's what it looks like now. The orange line is the original data that I collected from the Bureau of Prisons. The blue line is the inferred actual distribution of sentences. And as you can see, there are actually many more short timers. The most common sentence is actually a year and a day. But they're not in prison very long, and so they don't show up in the data very much. Now, here's where this gets interesting. We figured out if you're like a judge and you see every sentence go by, you get an unbiased view. If you visit a prison once and you take an instantaneous sample, you get the purely biased view. But what do you see if you're there for an interval of time, like 13 months? You're going to see something in between those two views. And in particular, it works out that if your inspection process is for a duration t, and there's a prisoner with a sentence length x, your probability of sampling them is proportional to x plus t. So that when that's small, that converges to the completely biased view, and as it goes to infinity, it converges to the completely unbiased view. But we can compute in between what it looks like, which is to take x, which is the same 85% of your nominal sentence, and t, which is the amount of time that you're in prison, so 13 months converted into years. And so the weight is x plus t. So I now take my unbiased view, apply these weights, and I get the green line. So just one more time, the blue is the unbiased. Orange is what you would see if you just arrived with an instantaneous snapshot. And the green is what you would see if you were there for 13 months. Now, interestingly, it's not very different from the instantaneous view. You actually have to be there for a very long time before you start to converge on the blue line. This also happens in multiple dimensions, but even more so. So in 2 dimensions, you get a linear weighting. In 3 dimensions, you get a quadratic weighting. And as you go up to n dimensions, you get a weighting of x to the power of n minus 1, which gets really big. And this is the basis of a claim that you might have heard, which is that if you have a multidimensional distribution, all of the probability mass falls in a thin shell that is not at the origin. It's not at the mean. Now this, I'm not going to explain too much of this today. This is what that looks like in 2 dimensions. If the unbiased distribution is a pure Gaussian, so that's just half of a normal distribution there, the biased distribution is the orange line. And as you can see, the most likely value is not at the center at 0. The most likely value is away from the origin. If you're curious about that, I decided to kind of skip over that today. But you can look in my blog. I have an article there where I wrote about that. This is the dartboard paradox. And the notebook that I sent you to also has the details in it. So to summarize, again, this kind of length-biased sampling pops up in a lot of domains. And it has different names in different domains. But my impression is that it's not super well known. But once you become aware of it, you start to see it everywhere. And you can think of it as a chance to do some clever experimental design. Before I let you go, let me just point out, if you want to read more about some of these examples, the class size is in ThinkStats, which is available as a free download. And the red line example is in ThinkBayes. If you have friends who are a little bit less technical, they might like this version, which is written for a kind of a more popular audience explanation of this. Now, I published this article, and nobody asked about the picture. So why is that the picture for this article? It's a paradox. Couple of quick public service announcements. The PyData group in Boston has been kind of quiet for a little while, but is ramping up again. So if you live in Boston or you're visiting, help us get this going. There are a few thousand members already, and hopefully some events coming up soon. You can also help me figure out what to do during my sabbatical next year. I have an article here that explains what I am capable of doing, and your job is to tell me which of those things I should do. So help me out there. And if you would like to get in touch with me, there are 5 different ways that you can do that.
Nice.
So, questions, thoughts, what do you think? Yes.
So I found in all of your examples, some of them I was able to get almost immediately, and others it took me a while, and then I heard your explanation, and then either I got it immediately or like it took me a couple of seconds and then I got it. And obviously this is super useful to think of in experimental design. Do you have any tips on things to look out for? Like, should I be looking for things where I'm looking at time or looking at distance? What are some tips and tricks to find?
Good question. Let me repeat it. So your observation is that some of these examples were obvious. Some of them it would take a minute and then it would click. And others you're kind of like, ooh, I might have made that mistake, if I'm paraphrasing. And so you're asking, so is there like a checklist that you can go through, which is if you're measuring things that are in time or space, should the light bulb go on, say, oh, I better watch out for length biased sampling. I might put it on my to-do list or my checklist along with all the other kinds of sampling bias. So, I gave the examples earlier of, you pick a group of people, they're not necessarily representative of the US population if that's what you're trying to measure. So I guess it's on my list of think about sampling bias and maybe just add inspection bias as one of the checklists. Other thoughts or questions? Yeah.
In the world of financial data, we often talk about survivorship bias.
Yeah.
So it's kind of like your people with no children don't answer the question in this room.
Yes.
And I'm wondering if that's just one end of a spectrum, and you just described it in the spectrum for us.
Great question. Again, let me paraphrase it. So you're saying that this is reminding you of survivor bias, that very often when you try to sample a population, there will be people who aren't in that sample exactly because of the property that you're trying to measure. Now, in the case of survivorship, it's kind of binary. They are either there or not, depending on whether they survive or not. And in this case, it's a continuous degree of oversampling. But yes, there's a connection there, and maybe add that to the checklist, survivor bias. Yeah?
Do you have an opinion on how to interpret the doomsday argument?
Do I have an opinion about how to interpret the doomsday argument? What is the doomsday argument?
So from Wikipedia, it's a probabilistic argument that claims to predict the number of future members of the human species, given an estimate of the total number of humans born so far. Simply put, it says that supposing that all humans are born in a random order, chances are that any one human is born roughly in the middle.
So assuming, if you think of everyone who has ever been born or will ever be born, on average, you should expect to be in the middle. And if it's like an exponential growth, then you should expect to be very close to the end. Is that what you're getting at?
Right, and depending on how you interpret it, you end up with a very different view about how long we have.
Right, so depending on how you interpret it, you'll come to a different conclusion. Now, I'm wondering how much the exponential growth assumption is built into that. Because if that's not true, if we get to a steady state or even start to roll over, then I think it's not the case anymore, that we should assume that we're near the end. And in fact, on global population, it looks like that's where we're headed. It looks like we're going to peak around 2100, and then global population will start to decline. So, I don't know, I'm just making stuff up. Good. Other thoughts or questions? All right, thank you very much.